This discussion serves as kind of a segue or a transition between our phylogenetics unit, which is most of Unit 1 and overlaps a little bit here into Unit 2, towards moving on to other molecular evolution topics. I know many of you are going to be sad that we're leaving phylogeny behind, but it's important. We've got other things to do. So a little bit of this is review, looking back, reminders, and then kind of a final couple important concepts as we look at an overall big picture of relationships among organisms or among different species, right? Because that's what a phylogeny is. It's trying to reconstruct something that goes all the way back to the very heart of evolution, that all living organisms share common ancestry. And so phylogeny is an attempt to understand, map out, and diagram all of that shared history. And so you know this already, but if a group of organisms is monophyletic, then we know that they share a single common ancestor that is unique from all of the other ancestors to all the other living organisms, and that says something unique about that group. And so similarities that we see across that group or widely distributed from within that group almost certainly came from that ancestor, and so they're unique to that group. Many groups are classified and then named based on the characteristics that define them as monophyletic. And today we have large genetic databases to either support many of those things, which have been understood sometimes even for hundreds of years, but also to revise and discover areas where people made mistakes. And today we're going to be talking a little bit about why some of these past things were mistakes. And so when a non-monophyletic group is put together, in this case paraphyletic, right, because we have two very distantly related branches and we have to cut out all these close relatives before we get down to the common ancestor. So that's polyphyletic, right, because there's more than one clade that we'd have to cut out. So non-monophyletic, polyphyletic in this case, sometimes those were classified in the past and they were mistakes. We're going to look at two examples of non-monophyletic groups and talk about why. So the first is maybe the most famous, very, very common, a paraphyletic group, quote unquote, the reptiles, the crocodiles, lizards, turtles, maybe we throw another one, so right, snakes are closely related to lizards, right? If you look at it, actually, it turns out that lizards are a paraphyletic group with respect to snakes because snakes are just really highly evolved lizards and are more closely related to some lizards than others. And we see that pattern over and over and over again. Here we have birds, which are just really highly evolved reptiles and should have been included in the original classification for reptiles. But they were not, and so reptiles is paraphyletic because we left out that branch. Birds, more closely related to crocodilians than they are to the other living reptiles. And so we can't have a group like that without including birds in it. Okay, hopefully you understand that. That's a bit of a review. And of course, the reasons for this are pretty obvious. There have been long branches, lots of evolution and many morphological features along the bird branch, right? So birds look very, very different from their ancestors. If you're to put a crocodile and a bird, find their common ancestor, crocodiles have many more overall morphological similarities to that common ancestor. Lizards, right? Same thing, morphological similarities. Snakes, despite losing their legs, still have many morphological similarities to that common ancestor. But birds have evolved very, very rapidly and have lost some of those morphological features. This, by the way, is one of my favorite birds, a shoebill stork. Look them up. They're very, very cool. And if anyone ever says, well, I don't believe birds are reptiles, or maybe even better, right, birds are dinosaurs, because birds are more closely related to the raptor dinosaurs, T-Rex, Velociraptor, all of those two-legged carnivorous dinosaurs. Birds are just a close relative of those. And so they really are not only reptiles, they're also dinosaurs, the only living group of dinosaurs to survive. And if anyone doesn't believe you, show them the shoebill stork, right? It's quite phenomenal. This is one that looks like he's about to eat you. Okay, but birds were not recognized as reptiles, number one, because they evolved and look quite different from their ancestors, so rapid morphological evolution. And then number two, also, many of the lineages that would have helped us to connect them and include them into the reptiles, those lineages were extinct. And it's not until recently that we've had an extensive enough of a fossil record to find support for this bird dinosaur and thus bird reptile hypothesis. But the molecules, the molecular data very, very strongly support that. And people are beginning to figure it out because of fossil evidence and reevaluation of morphological characters, even before we had well-supported molecular phylogenies. But the fact that we do just is kind of like extra support for this idea. And so we need to make decisions about higher level taxonomy once we have well-supported phylogenies, and so we revise it. And so today, the group Reptilia, although it's kind of more less of a formal term, we probably would say diapsids, now includes the birds. So we didn't just get rid of it, we now recognize. And we didn't get rid of the term dinosaurs because that was well known. We just now recognize that birds are part of the dinosaur group. And in fact, you might hear people refer to the non-avian dinosaurs. That's everything else except the birds. It's kind of a long, clunky way, but that's kind of the old school traditional dinosaurs are really just most of the dinosaurs minus the birds. Okay, so just be aware of that, and this is important. Now, a quick word that's not really related to phylogenetics, but I guess it's tangentially related. Higher level taxonomies, I hope you realize, are not equivalent. So if I look at a genus of insects and a genus of birds, those, even though those two groups have the same name, they're both genera, right? That's the plural for genus. They're really not comparable and equivalent. So really higher level divisions are monophyletic groups, but as far as how many or how old, how many species are included in or how old a genus is, there's no rule. It's really just whatever is convenient. And then we have genus, family, order, class, all the way up, right? And then many subcategories in between. But realize that although species are a real biological population, a phenomenon, a good classification, although you can't find a single definition for species, that seems to be a real thing that we can at least to a large extent compare one species to another. Genera, families, orders, classes, all the other higher ones really are not objective criteria. It's like there's no set of rules for what makes a genus. It can be one species, it can be tens of thousands of species. So just be aware of that. Now, one other last example. The old classification of vultures was polyphyletic. So as we begin to reevaluate morphological characters and evaluate all of the vast sources of molecular data that came in, it became very apparent rather quickly that the old group vultures was not valid. The old world vultures, like you see in The Lion King or in those Africa nature videos, right, in Africa and Asia and Europe, those old world vultures are closely related to the other birds of prey, the eagles, the hawks, the owls. Okay, so they're part of that raptor group. But the New World vultures, despite looking very similar to the Old World vultures, are only very distantly related. And there are some morphological clues to this, which we don't need to worry about, but the molecular data very strongly supports this. And it turns out the New World vultures, like we see flying around out here, the black vultures, right, buzzards, turkey vultures, or the California condor, the Andean condor, those are actually more closely related to storks than they are to the birds of prey. And in this case, it was convergence, right? So they're filling similar niches. They're both eating decayed material, so they have loss of feathers on their head to prevent accumulation of the nasty stuff they're eating in their feathers. They have that hooked beak for ripping meat. And so we see that those many convergent characteristics, which originally allowed or tricked scientists into putting them in the same group. And today, these are the Vulturidae. These have been given a new family name, and so we've just had to break them up and revise our taxonomy, right? So this was such a bad representation because of convergence, right? Where with the birds, it was a little different. It was loss of ancestral characteristics or plesiomorphies that made it difficult to put the birds in with the reptiles. There are other groups, too, that are largely recognized as grossly or very strongly polyphyletic. So, for instance, sometimes when people are trying to organize like a genus of insects where there are just so many different species, if they have a genus or a species within a genus, let's say, that is, well, let's do this. Let's say a genus within a family. So they have a genus, they know it's in this family, they have a species, but they can't decide where to put it. They don't know if it should go in genus A, B, C, or D. They will often have kind of what is like a trash can a genus, right? A genus that, if we don't know, we'll just stick it in there and try and figure it out later. So sometimes these polyphyletic groups are recognized and say, we just don't have enough data to fix it yet, but someday we'll fix it. So be aware of that, and it's an ongoing process of organizing, grouping, classifying, and naming all of these organisms. And that's the goal of systematics, and phylogeny is a very critical, important part of systematics. All right. Now, there are 3 reasons, and we're going to list them. I don't have them numbered here, but you should write them down in your notes. There are 3 reasons why a gene history might not match a species history. And by and large, we've been kind of just, inferring, assuming that it would, that if we can accurately figure out gene histories, putting together these matrices and figuring out all these complex ways to do phylogenies, that if we use those genes, they will give us the species history. And by and large, that's true, but there are some exceptions that we need to be aware of. The first one is gene duplication events, and you are already very clearly aware of this. So if we have a gene duplication event, it means we have paralogous copies or duplicated copies of an ancestral gene. And initially they're identical, they start to accumulate mutations and become different, but they're still recognizable and can be readily aligned to each other in a DNA matrix. So this could be alpha hemoglobin and beta hemoglobin, still very similar, and they accumulate more and more mutations as they evolve separately because they are no longer a single copy. But think about this. So if this is the true set of relationships, species A is more closely related to species B than it is to species C. This is, the outgroup for those two species. What would happen if we didn't recognize this was a gene family with two copies, and we sampled gene 4, gene 2, and gene 3? We just randomly sample those genes, we amplified them by PCR or something. Look at the relationships between gene 4, gene 2, and gene 3. If you trace them back, 2 and 3 are down this smaller line, there is where 2 and 3 share a common ancestor. So gene 2 and 3 are more closely related to one another than they are to gene 4, which doesn't connect back in until this gene duplication event. So that's just one example how if we don't recognize the problem of paralogy in these multi-copy genes, and if we have bad representation, then it becomes a problem and our gene history may not reflect our species history. Now today, with large sampling and better understanding of all of the duplication events in the big families, we can recognize these much, much more easily. And it's kind of cool because we can map copies back onto a phylogeny like this and see where they've occurred. And what we've found is that for some genes, duplication is rampant. So just as an example, and we'll probably look at this when we look at the molecular evolution near the end of the semester, opsins in insects are an incredibly diverse family of genes with multiple duplications and multiple losses over and over and over again. It's a very, very twisted and complex story that we have to tell. Okay, so number one reason why gene history will not match species history is if we have gene duplication events and we're mixing up paralogous and orthologous copies of genes. Okay, reason number two is called xenology. If you've had the introductory evolution course, you're already familiar with this, at least with this term. Xenology literally means ancient relationships or ancient association. Sorry, not ancient, alien. Alien relationships or alien association. Xenos is Greek root word for alien. And this means that we have a gene that has been transferred over from a very, very distant relative. And when I say relative, realize that that's a term that you can use for any organism, right? If I say, oh, look at that bacteria, it's your relative. That's true. Very ancient, billions of years ago relative, but it's still a relative. But notice that in bacteria, this is very common. It happens all the time, and also the archaea. So prokaryotes very readily transfer DNA from one species to maybe even a very distantly related species. And it happens in eukaryotes also, but less frequently. So it's not as much of an issue with eukaryotic relationships. But it happens so much among the bacteria and archaea that it really makes a phylogenetic analysis of these groups very, very difficult. In fact, some would say even not possible. In fact, if you want to try to infer more of a network-like pattern like this, where it looks like a web or a net, rather than a simple phylogeny like we have over in the eukaryotes. And here again, they try to put one rare horizontal gene transfer event. They do happen in eukaryotes, sometimes viral mediated, but they're rare enough that they are exception to the rule and usually don't have much of an impact at all on figuring out the phylogeny of this group. But for the prokaryotes, it's rampant. And so if we have a horizontal gene transfer event, we suddenly have a bacteria that can trace most of its genetic history down one lineage, but it shares some of its genetic history down another lineage. So we need more than one branch coming in to our quote-unquote tree, which is now really more like a network, right? So to represent a network, or to represent relationships among prokaryotes, we need a network or a web-like pattern, okay? So There are different methodologies. We're not going to talk in detail about these. We might mention them briefly and come back to them during our population genetics, because realize that this network-like pattern applies not only to phylogenies among different bacteria species, but it also applies to relationships within a sexually reproducing species. So you look at me and say, wait, what do you mean? Well, if you trace your own lineage back far enough, it might be 6 generations, it might be 100 generations. But if you do that, you're going to find that your paternal lineage and your maternal lineage, sorry, let me shut this down so we don't. Okay, so if you trace your maternal lineage, your mother's ancestors, and your father's ancestors, eventually you will find that they connect in at the same, you'll have your great-great-great-great-great-grandfather on one side might be your great-great, maybe 3 times more great-grandfather on the other side of the family also. And so we get that reticulation, which is a technical term, or that network-like pattern. So networks are better ways to show relationships between species of prokaryotes. They are also better ways to show relationships within a sexually reproducing species, like a phylogeny, or not a phylogeny, sorry, a genealogy of individuals in the human species. And I use one of the European royals because of all of the interbreeding that occurred in royals. They tend to have this network-like pattern much more strongly and much more recently among their ancestors. Because, you know, if you marry your cousin, right, or if you marry your niece, which happened actually more frequently than you might think among many royal groups, then suddenly your kids, right, any kids you have, are going to have that close connection on both sides of the family. Okay, so just realize that. So remember, number 1, gene duplication. Number 2 is xenology. And this pattern that's produced by xenology, a network-like pattern, can also be produced within sexually reproducing organisms. And that makes relationships within a sexually reproducing species harder to figure out and more applicable to a network-like pattern than a true phylogeny. Okay? Now, finally, is the third reason is what we were going to call lineage sorting. And to understand lineage sorting, we need to understand this idea of coalescence. Coalescence is when we have different alleles and a wider range of alleles, and it may take a while for them to coalesce into a single version of that allele, either through natural selection or through genetic drift. They will eventually. So if coalescence, and we'll talk about coalescence at a later time a little bit more, it has to do with the molecular clock also. But if speciation events are rapid and coalescence is slow, we could have multiple alleles. This diagram is not the best diagram to illustrate this. In fact, let me grab another one. Okay, this is a better image, one you're actually kind of familiar with. We introduced this in a very early lecture in the class. And we looked at how when we have multiple alleles, originally they're all the same. We have a mutation, now we have genetic diversity, and if it's a good allele or if genetic drift randomly chooses it, we end up with fixation of that allele. This process, if we look at it in reverse, is also coalescence, where all of the diversity represented in this population eventually coalesces into, and we can get back to one single ancestral allele. And we may have to go a little bit farther back, but I think maybe that allele right there represents, oh no, we got to go farther back, and maybe even more distantly. But we find the ancestor of all of these alleles. Now, what would happen if in this time period when they speciate, there's diversity? This one carries some black and red, and eventually red becomes fixed. This one carries some black and red, but then maybe either due to a change in the environment and a switch in natural selection, or again, sometimes genetic drift and random chance. What if we fixed the black allele instead of the red allele? Right? If that occurred, then this species C would have only the black allele, dating back to these guys, maybe a few mutations here and there, but still that functional black allele. These guys would have all the black allele, and these guys would have the allele represented by the red dot. And so if we were only using this gene, we might infer that species C is more closely related to species A, even though it's more closely related to species B. So that is called lineage sorting, and it's the third reason why gene history may not match species history. All right. So again, when speciation events are rapid and coalescence is long and drawn out, then it's more likely for lineage sorting to occur. Now, usually lineage sorting is only a problem among a few genes, but there are those cases where really, really rapid speciation makes lineage sorting more common. And so groups of organisms that speciate very, very rapidly, like the early birds. There seemed to be this explosion of species and many new groups popping up very rapidly when birds first evolved. Makes it very difficult to figure out the relationships because there's a high degree of lineage sorting. And so that can make it tricky to find the true species relationships. So again, review. Reason number 1 is gene duplication and the problems with orthology and paralogy. Reason number 2 is horizontal gene transfer, which we call xenology. Reason number 3 is lineage sorting, which occurs when genetic diversity is carried through into populations and then fixes in a pattern that's different than the relationships between the species. Okay, and again, this is not the best drawing, but they're showing how you have extinction. These are supposed to represent alleles, but they're descendants of each other. Anyway, it's a bad drawing, so use the other drawing. Okay, but the lineage sorting, the key amount of time is how long it takes for speciation to occur and how long it takes coalescence or allele fixation. If speciation is fast and coalescence or allele fixation is slow, you'll get lots of lineage sorting, and that makes phylogenies difficult to figure out. Okay. Now, the last thing I'm going to talk about, we won't go into it in detail, but I want to talk about consensus trees. Consensus tree is a way to take 2 or more trees and summarize them in a single tree that summarizes all of the relationships. This is a strict consensus tree, which means that we only show relationships that are present in all of the trees that we're trying to summarize. So notice in both trees, the B, which stands for baboon, is sister group to the rest. So in our consensus tree, we put baboon as sister group to the rest. Orangutan, O, is sister group to the remaining 3, so we put that there. But then tree number 1 and tree number 2 disagree about relationships within this. This is human, chimpanzee, gorilla, human, chimpanzee, gorilla. And so because they disagree, we collapse those down and show, yeah, they're separate from these other 2, but we don't know the relationships within this group, so we show it as a polytomy. All right, so sometimes a polytomy represents disagreement between maybe different analyses. Or it could also be that if we have one character that supports here and one character that supports here, parsimony can't decide. Equal characters mapped onto different branches would also result in that. But a consensus tree is an overview, okay? And there are different ways to do consensus trees. I'm not going to make you do consensus trees, so you won't have to figure them out if I give you subsets of trees, but I do want you to recognize them, and you'll see them frequently in the literature. We might take a parsimony tree and a maximum likelihood tree and a Bayesian tree, and then summarize them in a strict consensus, and then collapse down nodes where they don't agree. So you should be able to look at these 3 trees and see how we get there. We only show relationships that are present. And really the only relationship that's present in all 3 trees is this ABC group, which, although within it there are different relationships, A, B, and C, A, B, and C, A, B, and C are all part of a monophyletic group in all 3. So we represent that here, but then collapse the node down because there's one tree that disagrees with the other ones. 2 of them say AB, one of them says no, it's BC that are most closely related. And so people realized this was maybe a little bit too rigorous and that it didn't accurately reflect, because sometimes we have multiple trees that agree and just one of them disagrees. We still have to collapse it down under a strict consensus tree. And so a majority rule consensus tree does not collapse everything down, but it puts numbers showing how many of the constituent trees going into the consensus tree, how many of them agree. So in this case, 2 out of 3 are 66. This technically should be 66.66666%. But 2/3 of the trees support that AB here and here, so we put a 6, 7. And that one was 100, so we know all the trees support that group. And this one, with D being more closely related to A, B, and C, that node right there is again 2 out of the 3 trees, which is in this tree and this tree. And notice that even though the D being related to A, B, and C is in tree 1 and 2, and the AB together is in tree 1 and 3, so different sets of trees, it doesn't matter. We're just kind of going with majority rules. It doesn't matter which trees they appear in. And so you will see consensus trees all the time as ways to summarize different analyses, maybe done with different genes, or trees that were done with different phylogenetic methods. And so in a way, a consensus tree is kind of the very early way to do super trees. It's not quite a super tree, but it's maybe a similar idea where we're trying to summarize multiple analyses into one with a little bit of a formal analysis, but it's not a very tricky thing to do. And you can even do it by hand for these smaller genes. Sorry, for these smaller trees.